Yo, what's going on guys? Tanmay here for Simple Snippets and welcome back to another video tutorial on data structures and algorithms. And today is a very important video because today we're going to be talking about what is algorithm analysis. We're going to be taking a look at time complexity and discussing what is big O notation. So we are going to be talking in detail about what exactly is an algorithm analysis, which is as you can see over here. Then we're going to talk about why algorithm analysis is needed because this is very important to be answered. After that, we're going to be talking about the types of complexities and then focus on time complexity. And lastly, we are also going to talk about big O notation by taking some examples. Now, before we proceed, make sure you watch this video till the end. This is a request, and I can assure you guys that by the end of this video, this topic of algorithm analysis and what is big O notation and what is time complexity and all these different jargons that we have in data structures will be very clear. And this is a very fundamental topic, very important when it comes to interviews also, and also when you're learning data structures and algorithms. So please make sure you watch this video till the end. As I mentioned, I can assure you that I will make this topic very easy, and by the end of it, you'll understand everything. And we'll also take some practical examples. So this is not going to be just a boring theory video. Okay, so let's start off with what is algorithm analysis. So I'm assuming that you already know what is an algorithm. If not, we've already discussed that in this data structures and algorithms course. I will drop the link in the video description to this entire course. You guys can check it out. But then what is algorithm analysis? Now the word analysis should already give you a little bit of hint. But a simple definition over here is algorithm analysis is the study to provide theoretical estimations for the required resources of an algorithm to solve a specific computational problem. That is basically calculating the efficiency. So when you put it this way, it makes sense, right? So ultimately an algorithm which is running on your computer, which is running in your PC, is going to take up some resources. For example, it will take some memory, it will take some time to complete its execution, and these all things are supposed to be studied in order to make some estimates. Okay, so algorithm analysis basically just helps us give some theoretical estimations. Now the reason why I have highlighted estimations is because we do not get an accurate value, because to find out accurate value is very difficult. And that's why we can only make some theoretical estimations using this algorithm analysis techniques, which overall gives us how the behavior of the algorithm will be. And we'll talk about that in detail as we move ahead. So as I mentioned, generally, the efficiency of an algorithm is related to the input length, that is the number of steps, also known as time complexity, or volume of memory known as space complexity. So it makes sense, right? If your algorithm has 10 steps, it would take some particular amount of time, but if that step increases, let's say it becomes 20 steps, obviously the time also will increase. So it makes basic sense, right? And again, the space complexity also deals with how much memory your algorithm is occupying in memory when it is running. So whenever you're running a program, it is occupying some memory in the RAM. So that is space complexity. So we are going to be focusing on time complexity in detail, and we'll talk more, but I hope you've got a very basic idea of what is algorithm analysis. So with this idea in mind, if you want, you can take a screenshot. Let's move ahead and understand why do we need algorithm analysis, because that is very important. So when it comes to why do we need algorithm analysis, I'm going to put up two major points. So point number one, as you can see, is knowing the efficiency of an algorithm is vital on a mission critical task. So this makes sense, right? If you don't know how long your algorithm is going to take to execute or complete its execution, if your task is mission critical, then you might land up in some serious trouble. So to make it clear, let's take an example. Let's say you're working in NASA or you're working in ISRO or SpaceX, and these companies basically launch space rockets and satellites into space, right? So let's say you're writing an algorithm or writing a computer program which is basically going to take this rocket into orbit and release the satellite at a particular height. And when it reaches that height, you basically have just 10 seconds for the rocket to eject the satellite. Okay? So this is the problem statement, and now you need to write a program. Now if your program takes more than 10 seconds, your rocket will not eject the satellite at the right moment, right? And the satellite will get lost in space. Now you can understand the gravity of the situation, right? The seriousness of the situation. If your rocket ejects the satellite too early, it might fall back due to the gravity. And if your satellite is ejected after 10 seconds, it will get lost in space. So you can see how mission critical this task is, that you have to execute your program under 10 seconds only. So 10 seconds is your maximum limit. So that is the reason why you need to know how much amount of time your algorithm will take, or at least have a rough estimate about the maximum time, right? Another example can be the ejection of airbags in a car. So nowadays cars are equipped with airbags. So whenever you meet with an unfortunate accident, these airbags eject and they save human lives. Now obviously there must be some algorithm which is written behind which detects that there is a crash happening or there is an impact, and then it ejects those airbags on time. Now imagine if that algorithm takes more than 2 seconds. Now accidents happen in like less than 1 second, right? If your airbags does not get ejected in time, a person's life might get lost. So this is a very mission critical task, and hence you need to know exactly or at least have a rough estimate about the maximum time the algorithm or the program would take to execute or complete its execution. So this was point number 1, and the point number 2 is even more important or even more interesting actually, and that is generally there are multiple approaches or multiple methods to solve one problem statement. So algorithm analysis is performed to figure out which is a better or optimum approach out of the different options for us. For example, there are 3 different ways in which you can find out a given number is prime or not. You know what, you can just go ahead and Google it out and let me know in the comments below which is the most optimum one. Another example can be there are like n number of ways in which you can reverse a string. So all of them are different approaches, but they're doing the same thing. And we are also going to see an example as we move ahead in this video about an example which has 2 different approaches to do the same thing. Make sure you watch this video till the end. I know I'm reiterating it because it is very important, and this video is probably the most important one in the data structures series. So that's why I'm constantly telling you guys to watch this video till the end. So I hope you're getting that since there are multiple approaches, we need to figure out what is the best for us, right? So that's why I said better or optimum. So when I say optimum, it does not mean the best. Let's say for example, I have a computer system which has 10 GB of RAM and you have a computer system which has 20 GB of RAM. Okay, we are just taking basic assumptions. So we both have the same task, but you can see that since the RAM that I have is limited, my algorithm needs to be primarily thinking about the space complexity. So maybe I can get away with a little extra time, but I need to save space. However, in your case, since you have so much RAM, you are not worried about the space. So what you are more focused on is how fast can your algorithm run. So different situations require different criterias, and that's why when you have multiple choices, you need to select the one that is best suitable for you. So these are 2 major reasons why we need to have a good algorithm analysis. So talking about multiple approaches, what makes an algorithm better, right? Let's have a look. So the next obvious question arises, what does a better algorithm mean? Does it mean it is faster, which means it requires less execution time? And that's basically time complexity, right? So we're also going to talk about time complexity more when we go to big O notation in this video. Just hold on. Now another criteria can be less memory. Is your algorithm taking up less memory compared to some other algorithm doing the same thing? So that is dealing with space complexity. Now generally these first 2 criteria are the most focused on because those are the most important ones, especially the time. Nowadays our computer systems have lots of memory, so we don't really focus much on memory, but we are more interested in reducing the time. So we want our algorithms to run very fast. You don't want your website to wait like 10 seconds to load all the data, right? You want it in seconds. Now some other things that may be considered for a better algorithm is the algorithm easy to read? The readability of the algorithm. Is it having less lines of code? So let's say an algorithm A is doing the same thing in 10 lines, whereas my algorithm is doing in 20 lines. So maybe your algorithm is better. Another criteria can be, is your algorithm requiring less hardware and software requirements? So nowadays you must have seen that some programs only run on Windows 10. They are not running on Windows 7. So you can see that some programs also have software requirements. So it's not just hardware requirements. So as you can see, there are so many different things, and that's why you can see there is a note over here. Algorithm analysis does not give you accurate or exact values. However, it gives us estimate which can be used to study the behavior of the algorithm. Now because there are so many different criterias, there are so many different conditions, you cannot pinpoint and say that my algorithm is gonna run in exact 2 seconds. Because let's say you and I have the exact same laptop, exact same specifications, all the hardware and software specifications are exactly same. However, on your system, along with your algorithm, you have 10 programs, but on my system, I don't have any other programs. So CPU is directly only gonna focus on my program and my program will execute faster. So you can see just by addition of extra programs in your system, even though everything else was same, still my algorithm ran faster, right? So you can see there are so many different criterias. So that's why algorithm analysis does not give you accurate values. Now this takes us to the next big question, that is, Then what is asymptotic algorithm analysis? Now we've understood overall what is algorithm analysis. Basically studying the time and space complexity, how much time the algorithm takes, how much space the algorithm takes. So we have a category of analysis which is known as asymptotic analysis. So let's take a look at that. So when you're studying data structures and time and space complexity and this algorithm analysis, you must have come across this asymptotic algorithm analysis concept, focusing more on asymptotic word. Now the definition can be as follows. So in mathematical analysis, asymptotic analysis of an algorithm is a method of defining the mathematical boundaries of its runtime performance. So quite a lot of big words are used over here, but over here you can see in simple words what it is doing is it is used to mathematically calculate the running time of any operation inside an algorithm. That's the easy way to put it. So what happens is when you're measuring the performance, you want some numbers, right? So ultimately it is basically mathematics. So what we're doing is we're using this technique to define the mathematical boundaries. When I say boundaries, it means the upper and lower limit of an algorithm of its runtime performance. So runtime is basically the time required for an algorithm to execute. And now you can see that asymptotic algorithm analysis is more dealing with the time complexity. So you can see point over here, asymptotic algorithm analysis is used to estimate the time complexity function for arbitrarily large input. So when you're talking about algorithm, if everything else is kept constant, when I say everything else, it means the PC, the hardware, the CPU, the RAM, whatever hardware things you're using, whatever software you're using, if all those things are constant, which in usual cases are constant in an environment, the only thing that changes is the size of the input, which means how many number of steps are there in the algorithm. So that depends upon what input you give to that algorithm, right? And you'll see that if you're confused, you'll see this in the very next slide or as we move ahead in this video. So hold tight, don't get confused. So essentially we are studying the behavior of an algorithm for a large input to study the mathematical boundaries. For example, we are studying how an algorithm performs when it has 1000 steps or 10,000 steps because we want to study its boundaries, okay? So using the asymptotic analysis, we can easily estimate about the average case, best case and worst case scenarios of an algorithm. So when I'm talking about average, best and worst case, it means the time, okay? So the best time in which the algorithm can execute, that is how fast can an algorithm execute, how slow can an algorithm execute, and what is the average case, okay? So ultimately, time complexity is a computational way, basically a mathematical way to show how runtime of a program increases as the size of the input increases. So you've come across time complexity quite a lot in this entire slideshow. So most basic definition is it is a computational way to show how the runtime of a program increases as the size of the input increases. So how means the behavior. So let's say there are 10 steps in an algorithm. For 10 steps, how many seconds or microseconds is the algorithm taking? If I double that steps, if I make 20 steps, is it increasing linearly or is it increasing exponentially, right? So that is what we are trying to find out. That is what asymptotic algorithm analysis is helping us do. Now I know this was a lot of theory, right? So let's actually take some example because then we can easily jump on to the next big topic, that is big O notation. Okay, so as you can see on the screen, I have switched to our digital blackboard and now we are actually going to take a practical example to understand asymptotic algorithm analysis and understand what is big O notation. Okay, so what is the problem statement over here? Now we've been given a problem statement over here which is write a algorithm / program, which we are kind of assuming one and the same thing. So essentially what is algorithm? It is just step-by-step process, and when we convert that algorithm into programming code, we call it program, right? So we are assuming it as one and the same thing. So what we have to do is we have to write an algorithm or program to find the sum of n numbers. So n numbers would be ranging from 0 to n, and this n is supposed to be accepted from the user. So we'll take n from the user. Let's say user enters 3. So it would be 1 plus 2 plus 3 and the total would be 6. So we have to print out 6. Okay. So that is the problem statement. If the user enters 5, it would be 1 plus 2 plus 3 plus 4 plus 5 and then we have to print out the total. So I hope you've understood the problem statement. It's basic. Now to solve this problem statement, we have multiple approaches. If you didn't know that, you can Google it out. But let me just show it to you right now. So here's algorithm number 1 or method number 1. You create a function, and this is not exactly any kind of programming code. It is kind of like a pseudo code, but it's pretty understandable. You're creating a function. you're naming the function as sum of numbers and you're passing arguments as n. So this is something that the user will enter. First step is you declare a variable sum, assign 0 to it. Second step is a for loop. Now you run a loop from 0 to n, or you can say 1 to n also. And then you say sum is equal to sum plus I, and all the values stored in the sum variable itself, and ultimately at step number 4 you print the sum. So if you enter 3, your for loop will run from 0 to 3, that is 4 times. Okay, you can also run it from 1 to 3, it would run one time less, but that's okay. What will happen? Initially sum would be 0, so it would be 0 plus I is 0 for the first time, so 0 will be stored. So next time it would be sum, which is 0 plus I will become 1, 0 plus 1, so 1 will be stored over here. Next iteration it would be 1 plus I will now become 2, so 3 will be stored over here. For the next iteration 0 will become 3, so it will be 3 plus 3, so 6 will be stored over here. And now the loop will exit because I will become 4, we are only interested in running from 0 to 3. So after this we will print the value of 6. So basic enough. Now what we will do is we will assign some time for individual instructions. So you can see this algorithm is nothing but a step-by-step instructions. So we have instruction number 1, 2, 3 and 4. So let's assume this first instruction is taking 1 microsecond. Now we are just making some assumptions. Obviously every instruction is going to take some time, but it is not going to be 1 microsecond. I'm just making an assumption, okay? But obviously every instruction is going to take some time. Let's say this second instruction is the initialization of for loop. It will also take some time. We'll again assume it as 1 microsecond. Now this third step is totally dependent upon this n value, right? Because whatever value we enter over here, let's say we enter 5. So this for loop will run for 5 times. If it starts from 1, let's assume it is starting from 1. It will execute for 5 times from 1 to 5. If we enter 6, it will run for 6 times. So for this, let's say one step running it for one iteration takes 1 second. So for n iterations, it will take n microseconds, right? And then again, this last step is just printing the sum out. Let's assume it takes 1 microseconds. So after assuming all these values, we can conclude that the time required by this algorithm is something like n plus 1, 2 and 3 microseconds, right? And this 3 microseconds is always going to be constant. Only this n is going to be a variable. So this is that n. I'll do a small n for time and capital N for size. So this n will keep on changing. So depending upon this n, the time will change, right? So you can make a clear observation over here and you can make a graph of this. So how will the graph look like? So as you can see over here, this is how the graph would look like for this algorithm 1. So what is this graph? On the x-axis, we have the n value, which is whatever value entered by the user. So 1k is basically 1000, okay? So I'm assuming it for large numbers. If the user enters 1000 over here, this inner step will run for 1000 times, right? So this would be 1000 seconds. So it would be 1000 plus 3 microseconds. So ultimately it would be 1003 microseconds. Now again, I'm telling these are just estimations. These are not actual values, but this is something that would happen, right? In reality also something like this only will happen. So over here you can see that for 1k value of n, this y-axis is basically the time in microseconds. Okay, so this is in microseconds. For 1k it is taking 1 microsecond. So we are assuming it is taking 1 microsecond when you enter 1000. When you enter 2000 as sum of 2000 numbers, it is approximately taking 2 microseconds. It is a little above 2 microseconds because obviously we cannot have exact values. We've just talked about that, and you cannot never estimate exact values. For 3k, if you enter 3000, that is sum of 3000 numbers, it is somewhere taking 3 microseconds. And you can see that this trend is going in this direction. So this basically is called a linear behavior. So when I say linear behavior, it means that as the size of the input increases, obviously this n is representing the size of the input, because n is basically corresponding to the number of times this for loop will run, right? So if n is 10, this for loop will run 10 times. So we have 10 steps. So that is basically the size of the input. So as that is increasing, you can see the time taken by this algorithm to run is also increasing. And it is increasing in a linear way. So you can see this is a straight line which is going up and up as the size of n increases. So this is a linear way. So for this algorithm, the time complexity you can say is linear. Okay, so that's why I've said linear. Let's take the same problem statement and let's see one more algorithm for the same problem statement. Okay, so as you can see on the screen, this is algorithm number 2 and it is surprisingly very small. So you're wondering, okay, is it doing the same thing? So again, the same function sum of numbers, it is taking n from the user. However, in step number 1, we are declaring a variable sum and we are saying it is equal to n star n plus 1 the whole divided by 2. So where did I get this? Now this is a mathematical formula for calculating sum of n numbers. So for those who don't know, it's a mathematical formula, you can Google it out, and that is the reason why you have mathematics in computer science and information technology oriented domains also. So whenever you're going ahead with a course of IT or computer science, students generally complain about why do we have mathematics. It is for this reason. Okay. So you can see directly at this step itself, we are directly getting the sum, and at step number 2, we are just printing it. So again, if the user enters 10, we simply substitute 10 over here, 10 into, again, 10 plus 1, the whole divided by 2. If the user enters 100, we simply have to substitute 100. So you can see there is no for loop or there is no multiple iterations. We are simply entering this value inside this formula. It's that easy. So let's assume this takes 2 microseconds, okay? And this step takes 3 microseconds. So no matter what input you provide, if n is 100 or n is 1000 or 10,000 or 1 lakh or whatever the value, this step is only going to take around 2 microseconds. I'm not saying it is going to take exactly 2 microseconds, but it won't take a lot of time, right? It would take 2 seconds or 3 seconds or something like that. So you can see even when the n number is increasing, the total time over here you can say that t is equal to this 2 seconds or 2 microseconds plus this 3 microseconds, or we can just consider it as 1 microsecond because printing does not take a lot of time. So 2 plus 1 is 3 microsecond. So no matter what the value of n, your algorithm is taking 3 microseconds, which is constant. So this is some weird behavior, right? This is not the same behavior as algorithm 1. In algorithm 1, as the size of the n value was increasing, as this n value is increasing, the time is also increasing. However, here, no matter what the value you enter, your time is approximately gonna be the same. So how does the graph of this algorithm look like? So this is how the graph for this algorithm 2 looks like. Now you can see it is a straight line, however it is not an increasing line. So no matter what the size of n, so you can see n is over here 1k. So n is 1000. When n is 1000, it is taking 2 microseconds. When n is 2k, it is still taking 2 microseconds. When n is 3k, it is still taking 2 microseconds. When n is 4k, it is taking slightly greater than 2 microseconds because obviously it is not going to be accurate values. But you can see overall the time is not increasing. It is not increasing. It is constant. So this behavior is known as constant time behavior. Okay. So when you're doing analysis of algorithm 1, we are getting linear behavior. But for the same problem statement, we are typing or writing algorithm 2 and it is giving us constant time behavior. Now just by observing it, you can say that obviously algorithm 2 is much more efficient than algorithm 1. Now if you're still confused or if you're still wondering does it actually give the same value, let's actually jump to the code. Let's actually open up Dev C++ and type a C++ program to execute these two algorithms, and I will show you live what happens. Okay, so as you can see on the screen, I have already typed in the code because the algorithm was pretty basic. So this is the hash include iostream and the basic boilerplate that you have to type when you're typing C++ programs. So this is function number 1, or you can say this is algorithm 1. Let me just type it. And this is algorithm 2. So I have typed in 2 different functions, which are those 2 different algorithms that we just saw. If you want, I'll put it on the right hand side on the screen. You can see and correlate with the algorithm steps as well as the program steps. They are the same. This is algorithm 2. And in the int main, you can see I'm just declaring a double variable, which is double num. The reason why I'm declaring it as a double is because we are going to enter a large number, and then we are asking the user to enter that number. We're taking it from the user cin and we are passing it into either of these 2 functions. So function number 1 is sum of numbers 1. Function number 2 is sum of numbers 2. basically algorithm 1 and algorithm 2. Okay, so let's first call algorithm 1. Okay, sum of numbers 1. Save this, go to execute, and first let's just compile it. It will take some time. This is not the execution time, by the way. Now you go to execute and let's say compile and run. Okay, so as you can see on the screen, our program ran successfully because obviously I've already written it properly. If you want this entire code, I will share in the video description, but I would recommend that you type it. But now it is asking enter a number till which you want to find the sum. So let's enter a very large number. Let me go to the notepad and type in some large number. This is 100, 1000, 10,000, lakh, 10 lakh, crore, right? So this is 1 crore. Let's copy this and paste it over here. If I hit enter, we are directly getting the sum very easily because we still need to put a very large number. Okay, so this is 1 crore. Let's enter 10 crore, 100 crores. Let's copy this and let's try to again actually execute this and enter a large number. Okay, enter 100 crores. So if I hit enter and hit enter, you can see it is taking some time. 1, 2, 3, 4, 5, 6, 7, and you can see it took 7 seconds to execute, and I was literally counting it in front of you guys. So let's just do it again. Go to compile, go to execute and run. Let me just put it out properly over here. So I'm putting 100 crores as the number because it is a very large number and it should take some large amount of time. Paste. So this is 10 crores. If I hit enter and start the countdown, I'm gonna hit enter and start the countdown. 1, 2, 3, 4, 5, 6, 7, 8, and you can see it took around 8 seconds. So this is 100 crores. Okay, let's close this. Now let's come to our code. And so this was algorithm 1, which was linear complexity, which was when the time was increasing with the increased amount of size of the input. Now what we will do is we will run algorithm 2, which was a constant time behavior algorithm. So it was like no matter what the size you give, the algorithm was running in that exact time. Okay, so I'm going to make that change over here. We are calling sum of numbers 1, which was algorithm 1. So I'm going to make it to sum of numbers 2. Okay, save this. First compile it. Okay, make sure you compile it because otherwise the previous code will run. So I'm going to hit compile. It's compiled successfully. Close this, and now I'm going to say run. So now we are basically running method number 2. So we'll also see the output in method number 2. This output will be printed. Earlier it was method number 1. Let's come back to this notepad. Let's copy this number which is more than 100 crores. Copy. Come over here. Just paste it. If I hit enter and start the countdown, actually it will give us the answer immediately. It will not take 8 seconds. It will not take 10 seconds because it is constant time. It will not get affected by the size of the input. Let me just show you. Like I'm now hitting enter and there you go. Directly I got the answer. You can see method 2 sum of this large value is represented as like this in double, and you are also getting the answer in a large weird number. Don't go on the number, but you can see that when I hit enter, it literally printed out the output instantly. We did not even have to wait for 2 seconds. But for algorithm 1, we had to wait for 8 seconds. So you can see that this algorithm 2, which is of constant time behavior, was much faster than algorithm 1 for larger amount of inputs. So if you had to make a choice between the two, you would obviously go with algorithm number 2. And by the way, they are showing us the same results. Okay, so the output is correct. It's not showing some random values. You guys can put in some small numbers to see the actual output. Okay, that is the sum of n integers. Algorithm 1 and algorithm 2 will give you the exact same numbers or exact same output. So yes, this was a practical view or practical demo of how the algorithm time complexity changes with different algorithms which are achieving the same task. Now let's actually switch back to the digital blackboard. Okay, so now this actually brings us to the very last topic, which is one of the most important one of this entire video, which is the big O notation. So what is this big O notation? Now we just saw two different types of time complexities, which was linear time and constant time. Now similar to that, we have some more time complexities depending upon the behavior. So we have constant time, which we just saw. We have linear time, we have logarithmic time, we have quadratic, we have cubic, and we have n number of other different types, which if you want, I'll put a link in the video description. But in order to denote them in a mathematical way, we use this big O notation. Okay. So instead of telling this algorithm is linear time, or this algorithm behavior is quadratic, or this algorithm's behavior is constant time, we say big O of n for linear, okay, or big O of n square for quadratic time. So big O notation is nothing but the formal or mathematical way to express the upper bound or the worst case scenario of an algorithm's running time. So what it does is it measures the worst case time complexity or the longest amount of time an algorithm can possibly take to complete. So now you're wondering, okay, so if big O notation is measuring the longest amount of time, what is measuring the shortest amount of time? So we have other two notations also, which is omega and theta notations, but they are not as relevant as big O notation, because whenever you're running an algorithm, the most important aspect when it comes to time is you want to know is how long or what is the maximum amount of time the algorithm will take given a particular size of the input. You're mostly not worried about how fast it will execute, right? You're mostly worried about how much maximum amount of time will it take to execute, because that is more critical. You want to know the worst case rather than the best case. If you know the worst case, you can work around all the other algorithms to match that, and then you know that worst come worst, your algorithm will take 10 seconds or less. So that's why big O notation is very much more important and relevant. Not to say that others are not important, but big O notation is more important. So the way some asymptotic notations are is, for constant time we say O of 1. Okay, you can say O of 1 or big O of 1, that's how you say it. For linear you say O of n, which means that when n increases, the time also increases. It is linear. So this is that linear behavior that we saw. We have one more as logarithmic. We have quadratic, which is also known as exponential behavior. So when the n increases, the time increases the square times. So if n is 2, the time might be 4. But if n becomes 3, the time taken would be 3 square, which is 9. If it becomes 4, so n is the input size, this is n, and this is the time. So if it becomes 4, 4 square will become 16. So on a graph, if this is n and if this is basically the time, so the graph would look something like this. Okay, this would be 2, this would be 2 somewhere over here, then we have 3, somewhere over here, then we'll have 4, over here, and the time is going to be 16, this is going to be 9, and you can see there is an exponential growth over here. It's not linear, it's not like this, it's not a line, it's a curve. Okay, this is quadratic growth, or you can say it is exponential growth. Now one last question that comes into our mind is, how can we calculate this big O notation? Because now that we understand that big O notation is just a way to represent the time behavior of different algorithms, and we are just calculating the upper bound, how can we calculate it ourselves using basic algorithm analysis, right? So that is most important. So let's take our previous algorithms example itself and let's do this big O notation calculation ourselves. Okay, so as you can see, we have this algorithm 1 which we just saw previously, which was having a linear time or linear behavior, and now we can also denote it as O of n or big O of n, now that we know that linear is called O of n or big O of n. But why is it called O of n? So let's try to understand that. Okay, so I just shifted the graph over here. We don't really need the graph right now. We already know that it is a linear behavior. So how do you go about coming to this conclusion that algorithm 1 is O of n? So let's actually go step by step. So in the algorithm analysis, we know that this step is taking 1 microsecond. So we are making assumptions. It can be 2, it can be 3, but it is going to be some value itself, which is not going to change, right? So if this step is going to take 1 microseconds, it's always going to take 1 microseconds or something around that. For step number 2, the for loop initialization, let's assume again it is taking 1 microsecond. The inside for loop, this step number 3 will run for n times depending upon what the value of n is. So I'm going to say n microseconds. So it's going to get multiplied with n. This last step again, let's assume it is taking 1 microseconds. So analyzing this totally, the time, let me use another color, t is equal to 1 plus 1 plus 1, which is 3 microseconds plus n. So it is going to be equal to n plus 3 microseconds. Now the way you calculate big O notations, we have 2 basic steps. Okay, let me just show it to you. So these are the 2 steps when you want to find out big O notation by yourself in a practical sense. So it's not exactly how a systematic way goes when it comes to calculate big O notation. That can be a separate tutorial itself. You can Google it out also. But in a practical sense, you can also do it yourself just by studying the entire algorithm. And the 2 major steps are, First thing is we have to find out the fastest growing variable term in the entire equation. Now this has become an equation for time complexity. So this t is representing the time complexity. So in this equation we have two terms. This is the first term, then we have a plus in between, and this is the second term. Now looking at this, you can say that this 3 microseconds will never change. Whatever the n value, this 3 microseconds is because step number 1, 2 and 4 always takes 1 microseconds. So this can be considered as a constant, right? So I'm gonna write constant over here. However, if you see, this n is actually a variable because it keeps on changing. So we have to find the fastest growing variable. We only have one variable in this entire equation, right? On the RHS of this entire equation. So as whatever value of n you put, the time also increases because it is a linear behavior which we already saw. So this is the fastest and this is actually the only variable, right? So we found the variable. So what is step number 2? Step number 2 is we have to eliminate the coefficients and the constant terms. So over here, the only constant term is this, which is the extra time required for these extra steps, but they will always take some constant time. So that is the constant term. So what is this coefficient? So the coefficient can be some value attached with this n. Okay. Right now we don't have any value, but it could be something like t is equal to 2n plus 3 microsecond. Now this 2 is essentially a coefficient. Okay. It's a coefficient. This n is a variable and this component is a constant. So what we have to do, we have to find the fastest growing variable, which is n. So we found that, and we have to eliminate all the other coefficients and constants. So ultimately, the time complexity t will be equal to n, right? And it is also denoted as O of n or O of capital N or whatever the value over here. What is more important is the term that we are left with. We took capital N, so it would be O of capital N. Okay. So this is the time complexity, which is O of n. So this is how you found out the big O notation for this algorithm, which is basically having a linear time behavior, which is represented by O of n. Now quick note, these constants and these different coefficients can be added in any algorithm because, as I mentioned, whenever an algorithm is running in your system, it is not just dependent upon the number of steps. It is also dependent upon how fast is your processor, how fast is your RAM, what is the size of your RAM, is your processor 7 gen, is your processor 9 gen, right? What is the CPU speed of your processor? So all those things basically are these coefficients and constants which get added to this entire equation. And then ultimately we just have to figure them out and just focus on the fastest growing variable. Sometimes in an equation you have multiple variables also. So when it comes to quadratic kind of equations, it would be something like t is equal to n square plus 2n and so on and so forth. So in that case, which is the fastest growing variable? Obviously n square will grow faster than 2n when the n is very large, right? Because we are doing asymptotic analysis when the input size is very large. We want the worst case scenario. So in that case, we have to eliminate this part and we just focus on this n square variable, and ultimately we will end up with O of n square. So I hope you are understanding how we calculate big O notation by ourselves in a practical sense. And big O notation ultimately is nothing but a formal or mathematical way to express the upper limit of an algorithm's running time. So yeah, this was the entire video on time complexity, big O notation, algorithm analysis, asymptotic algorithm analysis, and I hope you've got a very clear understanding of all these topics. Please let me know in the comments what your views are. If you have any more confusions, if you want any more explanation, let me know in the comments. If you've understood this, please give this video a thumbs up. Let me know in the comments that you've understood it, because it is very important that I get your feedback. And as I mentioned, this video is very important. If you've made it so far, if you watched this video till the end, I would request you guys to subscribe, because there are many other video tutorials on this channel and lots more are coming soon based on programming and information technology and computer science tutorials. So that's it for this video, guys. See you in the next one. Peace.